Hello, everybody. Now let's take a look at problem 5.49. This problem gives you a circuit. The circuit has two different switches in it. Okay, so we have two switches that flip at two different times. We know the circuit element values. So we know the current, we know the resistor values, and we know the inductance of the inductor. So let's come up with some equations to find the IL, which is the current through this inductor right here. So let's figure out how to do this. So let's break this down and think about the fact we have two regions we could consider, right? So first we have this switch that flips and then this switch that flips. So let's think of this as two different circuits. One is this circuit before this switch is flipped, and then one is the circuit after that switch is flipped. So let's break it into that. Let's start in this region from 0 to 0.5 seconds and just assume that there's no other switch. So we can see that before this first switch is flipped, the inductor here was not connected to the rest of the circuit. So clearly there was no current in that, right? This switch previous to time 0 was open. And so it was open for a long time. There's no current in there, right? It's not connected to the circuit. Because the current can't change instantaneously, we know that the current at time 0 minus and 0 plus is going to be the same. So once the switch is flipped, after a long time, we know that the current is going to be equal to this current, which is the source current. And we know that because after a long time, right, nothing is going to be changing anymore. And so this inductor is going to be acting as a short circuit. So all of this current will go through the inductor instead of going through any of it going through the resistor. Then we can come up with a time constant because we know the inductance and we know resistor 1. Putting these all together, right, we have this equation for the current through an inductor. So let's call this L1 because this is the first part of the equation that we're going to write. It gives the current from 0 to 0.5. Okay, so we can just take our values now. We know the current at time 0 because this is equal to 0 minus and 0 plus are the same. We know the current at time infinity. We know the time constant. So let's put those numbers in, and we come up with this function that describes the current in the inductor from 0 to 0.5 seconds. Now, let's consider IL2. So now we need to look at the second part of the circuit when the second switch is flipped. So again, we're going to need to find the initial current, the final current, and a time constant. And then we're going to use that main equation for writing current in a RL circuit. Okay, so to find the initial current, let's say that the initial current for IL2 is equal to the current in IL1 at time equals 0.5. So we'll find IL1 at 0.5, and that's 3.11 amps. So this is going to become the initial current here. Now let's look at the final current. And just like in the previous circuit, we know that after a very long time of both of these switches being closed, all of the current is going to go through this resistor, right? So none of the current is going to go through resistor 1 or resistor 2 because this inductor here is going to be acting like a short circuit. So because the inductor will act like the short circuit after a long time, all the current will go through there. So we know the final current is going to be 4 amps. So that just leaves us with finding the time constant, which we know is the inductance over the resistance. Okay, so what is the resistance going to be? We have two inductors now, so it's going to be some kind of equivalent, two resistors. So we know it's going to be some kind of equivalent resistance. So if we just color code these, right, we can see R1, R2, they're obviously in parallel. So the equivalent resistance is going to be R1 in parallel with R2. So if we reduce that, we'll end up with time constant of 1/2 seconds. Now let's put this all in this equation and notice that for IL2, right, this starts at t at 0.5 seconds. So we're going to add in this time shift here. So we're going to add in the time shift here, and we're going to add in the time shift up here to indicate that this response begins to occur after 0.5 seconds, we'll put in all of our values that we got previously. So our final inductor current, our initial inductor current, and our time constant, right? So 1/1/2 is equal to 2. And this gives us the second current. So combining these, we now have a complete set of expressions for the current in the inductor when after switch 1 is flipped and after switch 2 is flipped. So thank you. I hope this helped you to understand how these time varying RL circuits work. Thank you, and I'll see you in the next video.